Hi, everyone. So I'm Jackie Gutman. I'm going to talk today a little bit about an approach to data science programming that we use at Flatiron Health to help us continuously monitor data quality in our oncology healthcare data. So specifically, data quality of dynamic longitudinal data. And so I'll kind of quickly introduce myself and the challenge that we've been addressing in kind of maintaining very high standards for data quality in data sets that are continually being updated, refreshed, and redelivered each month. And then I'll show how some approaches to structuring the data and taking a kind of functional approach to code development helps us to mitigate and simplify that challenge. There's plenty of seats like all over, so make yourself comfortable. Okay, so first a little bit about me. I joined Flatiron Health in January after doing data science and machine learning in a few different industries, including medical education, public school education, meal kit delivery services. So now I do the same thing, only but for oncology and clinical care. So just a little bit about the sort of problems and type of data that I'm dealing with here. Flatiron Health is a company that strives to improve lives by learning from the experience of every cancer patient. So practically speaking, that means a lot of data, right? Including data on over 2 million cancer patients in the United States. And that data gets updated on a continual basis. And every month we freeze and deliver that data to partners and clients, and we deliver it with a 30-day recency. So meaning that the time from a patient experience or outcome being observed in the electronic health record to the time that that observation is in the hands of researchers and industry leaders who can generate insights from it is only 1 month, which is really considered unparalleled in the world of medical research and real-world evidence. So something that will become very relevant to the data quality approach that we're taking here is that our company relies on close collaboration between technical staff with expertise in building, managing, and testing data pipelines, statistical and methodological experts who really love to dig into and evaluate the data, and clinical experts in oncology who help us to translate what we're seeing in the data to what that means in the real world for patients with cancer and oncology providers that are being described by the data. And so a little bit about where the data is coming to us from. Our data points come to us from a wide array of sources, including the more than 800 unique sites of care that use our electronic health record technology, as well as several academic medical centers, which each use their own electronic health record software, and they partner with us on converting that data into outcomes research. So one of our major data products are these kind of national longitudinal data sets of real-world oncology data, which we update and grow each month. So we currently deliver data sets on 20 distinct cancer types. These data sets have some shared but non-identical data structures. And part of monitoring the quality of our data over time includes tracking the changes to our data delivery from this month as compared to the previous month, as compared to 3 months prior or 6 months prior, and really being able to understand and draw conclusions about the quality and consistency of the data for each type of cancer as compared to other data marts that we've built out and continue to maintain and grow. So what does this mean for us? What is the challenge? We need a framework for detecting and monitoring unusual changes within and across variables, within and across cancer types, within and across patients, when we're looking at and comparing kind of different snapshots of our data frozen at distinct points in time. So we're not just looking at analyzing a single data set, but we're looking at analyzing many different data sets in tandem and sort of understanding the quality of each one relative to the related data sets. And so we need to be able to stand up any kind of data quality framework on an ongoing basis, right? So it needs to be able to easily be refreshed and updated throughout the month so that we can make changes to our data pipeline as needed. And we're doing this as the number of data elements within each data set are growing, as well as the number of unique data sets overall are growing, and growing at a pretty rapid pace. So in addition to that kind of challenge, we also really need to have reliable and readable code that can be collaboratively developed by technical and non-technical and clinical staff, all working together to kind of synthesize the methodological best practices with the clinical intuition of our research oncology experts. So there's many different frameworks and tools that go into this for us, but I want to specifically focus on some of the more generalizable learnings here that a few perspective shifts that kind of make this comparative evaluation of our data possible and make it possible in a sort of maintainable and scalable way. So in order to meet this challenge, we knew we would benefit from really codifying that statistical and domain knowledge into a library of modular functions. And we felt that these functions should be testable, they should be clear in intent, and they should be able to be composed into higher level, more abstract processes. And building out these function libraries sort of serves to both document and kind of enforce what we on the quantitative sciences team established as best practices for working with our data. Additionally, for the purposes of maintainability and fostering collaboration, we wanted to be able to decouple the high-level sort of checks and reasoning represented by the code from the low-level implementation details to make those checks really more transparent and interpretable to anybody looking at the analysis code. And finally, we wanted to ensure a flexible approach that could take reasoning and code originally developed for working with a single data set and kind of seamlessly extend it to analyzing many data sets simultaneously. And without breaking down when the structure of a new data set differs in minor but meaningful ways from historical data or from data derived from a different cancer type or patient population. So the way we approach this problem really borrows a lot from the principles of functional programming. And I think it's pretty easy for discussions of functional programming to quickly devolve into computer science jargon. But for our purposes in thinking about data science and data quality evaluation in particular, this definition really means a few key things. So most importantly, functions, lots of functions, and kind of functions as first-order citizens that we can treat as just like any other variable and pass these functions as inputs to other functions. So that allows us to kind of string together these functions into higher order functions that return new functions depending on the conditions and context of how we're using them. And next, that these functions or chains of functions with very clear declarative names kind of give us an additional degree of separation from the mechanics of the implementation to allow us to sort of abstract out what is being done from precisely how that process is being carried out under the hood. And then finally, that these functions should strive for some degree of purity in that they avoid side effects and dependencies on variables and states outside of the world of the function. So this gives us a kind of sense of confidence that no matter what else is in our environment, no matter what order we run the function or how many times we call it, if we provide the same input into the function, we're going to get the same output out of it. So one thing that's a little bit different about our approach to measuring data quality is, as I said, we're often working with many data sets at once. So whether that's this month's data as compared to the data we froze at the end of last month, or comparing the data from our advanced non-small cell lung cancer data as compared to the data for metastatic breast cancer, or data around sequences of therapy, as compared to biomarker testing data, we're looking at multiple distinct data sets that may or may not have similar variables. And so the way that we define quality measures is often relative to some other data set. So what we find is that working with nested data structures, where we may have a pandas data frame where one of the columns is itself made up of other data frames, or one of the columns is itself made up of connections to a SQL database, it's a sort of useful simplifying framework that helps analysts and data scientists on the team kind of transition from working with reasoning about a single data set to reasoning about many data sets at once. Secondly, as I kind of mentioned before, emphasizing library development rather than standalone analyses helps us support not just code reusability, but really creates a data science culture that promotes visibility of code between teams that are often siloed, and encourages the development of unit testing and function documentation as sort of primary to the code development process. And then finally, this functional approach really empowers a different kind of code review. So when we talk about code review, we're often thinking almost exclusively about software engineers and sometimes data scientists really checking the implementation of a particular piece of code. But on our cross-functional teams, we also want to ensure that those who are closest to the intention of the code are reviewing whether the approach we are taking is reasonable. So not just whether it's implemented correctly. So this style of programming can support a team structure where those with significant problem and domain expertise can kind of undertake a sort of conceptual code review, and those with considerable technical expertise can really focus on an implementation code review. So here's a little example of how these nested data structures I spoke about might work in practice. So we can build out a data frame that refers to several frozen snapshots of data taken at different points in time from different database schemas and tables, and possibly of different disease types in this case. And because data frames are the sort of fundamental structure that we're used to working with, this kind of comes naturally to us, and we can now treat individual data sets as we would individual observations within a data frame, and kind of whole databases of many data sets with their associated metadata as just any typical data set that we want to understand and analyze. So this kind of allows us to take a kind of simple function that we have developed as a data scientist to take in as input a single data set and output a single evaluation metric, and create from that a sort of set of higher order functions that return sort of composite evaluation metrics, and look at kind of changes in the quality and those evaluation metrics over time or between data sets. And we can do this kind of rather seamlessly across many dimensions and many data sets, because this is all stored within this kind of parent data frame. So, for example, here we might take a very sort of broad and generic function that executes a query against our database. And we might use the kind of notion of partial functions to sort of fill in some of the arguments to that function to make it do something a little bit more specific, right? So rather than just execute any query, we create a more specific version of that executes a query against the database that counts all unique patients in a data set, or executes a query against the database to return a list of all of the patients in that data set meeting a specific inclusion criteria. And we can apply that function to all the nested data sets within our parent data frame, the same way we might apply a function to all rows of a particular data frame. And again, you know, each data set might have tens or hundreds of thousands of observations, but the total number of data sets is probably in the dozens at most, right? And so we're not really particularly worried about kind of vectorization here, right? We're talking about something higher level that takes in as input an entire data set, rather than a single observation or set of observations. So starting from this structure, we can sort of begin to add complexity by chaining some of the functions together into larger data pipelines, or we can build in a kind of error handling to these component functions. But the functions themselves really remain pretty easy to develop for our data scientists because each function is still, at its core, usually taking in either a single data set or perhaps a pair of data sets to be compared. So I'll go through some more kind of concrete examples of what this approach to programming for data quality gets us, but we found the benefits can really be kind of broken down along these 5 dimensions. So first and foremost, readability, right? This approach really lends itself to readable code. Higher level abstractions that emphasize declarative intent over procedural instructions are more easily understood and sanity checked by our non-technical staff. So that supports the kind of differentiated code review we spoke about earlier. It's really clear to kind of look at this and see what it's doing, even if we're not sure about the actual details of the implementation. So this also provides a kind of self-documenting code where the function and variable names themselves really describe what is being done. And the actual process of function design then becomes a process where the implementation is aligned with the intention. And the intention should be rather clear from the function names. So compositionality. So another advantage that we see here is compositionality, which allows us to really string together simpler functions into higher level functions of increasing complexity without compromising the flexibility, readability, or testability of the component code. So in this kind of example, if we're working with pandas data frames as inputs, we can use the pipe function to compose functions into a larger pipeline of transformations or operations. And then we can kind of save that pipeline as its own new function in order to apply it consistently over multiple data sets. And we can generalize that to functions that don't just take pandas data frames as inputs, but any kind of arbitrary Python function. So either by creating our own sort of compose function, as we see here with the help of a functools.reduce, or kind of using the built-in compose or compose left functions in the tools library, we can take a sequence of operations like what we might see on the left where we're applying sorted and then add previous and then reversed and then to list. But it really needs to be read from kind of inside out and bottom up, and it's really counterintuitive to how we would normally read language. And we can kind of reverse that into a new and appropriately named function where the function definition of that new composite function can itself be read from left to right or top down in a more intuitively interpretable way. And perhaps there's even just a clear way to refer to that new composite function. So again, this concept of compositionality really supports the readability concept as well. So next, another important advantage we see here is reproducibility. So we want to really have confidence that for any analysis, running the same function with the same input should always produce the same result. So by developing functions where we avoid mutability, where calling the function changes the actual state or variables defined outside of the function, and preventing other similar kinds of side effects, we can really avoid hard to test for bugs. And we don't want the success or failure of our unit tests to depend on things outside of the actual function and its input. So this concept of immutable inputs and outputs and processes that are deterministic and always return the same result when given the same inputs, that's going to help increase the sort of reproducibility of our code. And then closely related to this, as I kind of alluded to, is this idea of robustness. So modular functional code that avoids this kind of mutability and side effects and external dependencies is going to be easier to test. And if we're using unit testing more effectively, we're going to be building more robust code in the long run. So code that is harder to test just won't get tested or won't get tested effectively. And so it will be more prone to unexpected errors. But that's unexpected errors. What about expected errors? The functional approach can actually help us here too by wrapping sort of unsafe, brittle functions with no exception handling, wrapping them in their own sort of try-catch exception handlers, where the new exception-handled version of the function gets returned as a new, newly named, more robust function. And that robust function can then be sort of mindlessly deployed in an analysis without breaking the functional flow of the code or requiring the analyst to think deeply about potential exceptions that might occur each time they're using the function. So again, the tools library here provides us with the accepts wrapper to turn any callable into sort of a more robust version that has its own bottom value, avoiding kind of the side effect of throwing an exception if an exception is hit. And then finally, efficiency. So this is kind of last on our list of benefits because for this particular use case, again, we're often much less concerned about gains in efficiency, and especially if that's going to come at the cost of things like readability, reliability, and robustness. It's not something we're typically optimizing for. But even so, there are ways to take advantage of lazy evaluation and caching of previously computed values in a way that provides us with improvements in efficiency as well. So here, for example, we can use a lazy MapReduce paradigm to iterate over chunks of records returned from a database in this particular case, which are pulled just in time from the database in order to apply some arbitrarily complex composite function to each chunk. And again, when we're sort of building out and developing the function, we might just use the generator to just give us one chunk at a time and make sure that the function is working as expected. And so we can, again, lazily sort of return each chunk, compute the aggregate result, and then use the map and concat functions from the tools library to power much of this kind of lazy evaluation. So this is like really just a sort of simple MapReduce type example. You probably would just do the whole thing in SQL, but if you had a more sort of complex function, you could use this sort of paradigm to do it in a similar sort of MapReduce style that would be lazily evaluated. And caching. So additionally, if we expected that over the course of an analysis, a function could be potentially called several times with the same inputs, and that function execution was itself kind of expensive, we might save some computation by caching or memoizing the results in a hashable dictionary using the functools LRU cache decorator. So we'll have this hashable dictionary, we'll hit it up on all subsequent function calls and only newly compute the result if it can't be found in the cache. So since we've designed our functions in such a way that we know they should always return the same the same output if they're given the same input, we can avoid the kind of duplication of effort of recomputing results for common inputs. And we can decide based on our use case how many recently returned results it makes sense to store in memory. So that's the kind of efficiency gain there. And then, yeah, that's it. You can find out more information about what we do at Flatiron and what kind of data products we build on our blog. And yeah.
Open up to questions. Is this working too?
I don't know.
I'll just run it to whoever.
Yeah.
I have a question. So, as you're collecting these data sets, there's a decent chance over time that you'll come up with, like, oh, there's a new column that we should be having in these data sets, or something will change in just the way that things
Yes.
go. So how do you think about, like, if you have these functions that take a data set as an input, and that input changes, or you have sort of heterogeneous data sets, how do you think about designing a library like this to handle those cases?
Yeah, so a few different things. So one is that we'll use for things that are always changing between many different data sets, right, we'll try to specify certain characteristics of the data in configuration files. But usually for things like where we, add a certain column at a certain point in time to a data set, and then from then on, that data set has that column, but prior to that date, it didn't have that column. Again, we'll often wrap a lot of these function calls in these sort of exception-handled versions of the functions, so that if we're hitting up, let's say, a disease that didn't exist prior to March, or if we're hitting up a variable that didn't exist prior to some other date, we can just sort of return NA, and there's no particular comparison to be made. Often what we're doing is sort of like comparing over the history of the existence of a particular variable or the history of the existence of a particular data set. How has that data set changed? How has that variable distribution changed? But we don't want the functions to be sort of brittle and just error out completely if that variable didn't exist at all. Yeah. Yeah.
I will project. First of all, this was great. Thank you. So my question was about, you mentioned early that it's been really important that any alerts raised by your quality checking are actionable and interpretable. And
yeah.
I also work in this space. I know that that's a really important thing. And my question is around how when you're trying to get that actionability right, are you targeting? Is it people with clinical expertise that are responding to these alerts, and do they have a really deep understanding of what is the very domain-specific, data set-specific thing that we're checking, or are these more engineers or operations folks that don't necessarily have the domain expertise? How did you sort of actually for whom?
Yeah, that's a great question. So we definitely have very sort of cross-functional teams usually reviewing most of our QA reports, and these alerts can sort of be filtered up appropriately. And so I think, usually the first kind of level of checking is sort of done at with people who are really familiar with the data model, and sort of like, oh, we know we just like changed the instructions that we gave to the people curating this particular variable. And so if we're seeing a change, maybe it's because of these new instructions that we issued starting last month. And if there's something that's not necessarily immediately apparent at the kind of data model level, like, we started like coding this particular derived variable differently, then we like filter that up to people with more both like clinical and like pharmaceutical understanding. So people who might know, there's a new change in the sort of like market history of a particular drug approval, or there's a change in something in terms of the disease or testing that's being done that could explain. And so I think we really try to have people at kind of all functions in our company involved in sort of being able to find a kind of underlying reason for that change.
I see. So one follow-up. So is it true that mostly the case is you'll get new data and then you sort of have a 30-day window before you need to pass it on to the next person. So you're kind of in a lucky spot where you don't have to anticipate or prepare your data pipelines for those changes that you described. You can detect that certain things have changed to the data and you have 30 days to get them handled. Is that true? So you're mostly reacting to data quality issues rather than trying to prevent them?
Yeah, I would say that sometimes we are reacting to them, but there are certain kind of quality issues that they're really not apparent on the sort of month-to-month basis. So the sort of like most critical checks we do are comparing this month to last month and sort of making sure, like, did we just stop getting documents from this particular provider? And so this variable is always missing from, this particular source. And those are the kind of like highest priority sort of checks, but there's a lot of more subtle changes that when we're sort of like reviewing things on a month-to-month basis, it's not really apparent that anything unusual has gone on. But when we start looking at things like maybe this month as compared to 6 months ago or something, there might be changes that start to emerge. And so those might be things that, depending on the severity of them, don't necessarily need to be like immediately alerted to our clients, or it doesn't necessarily mean that we need to interfere with the sort of delivery of the data, but ultimately like something needs to be sort of better understood and addressed. Yeah. Yeah.
I'm interested in if there's any extra friction in your onboarding process. I find functional programming to be a very different way of thinking about problems, and I think that's true for especially a lot of people starting to program, and there's a lot of data scientists who are coming in without necessarily like a full computer science background.
Yeah. So this is an interesting question, and at this point I will admit that actually most of my team programs in R. And so we are, for the most part, at this point, developing these libraries of functions in R. And I think it's a little bit more common to accept this sort of functional programming paradigm coming from a language of R. And so maybe that is one of the reasons that kind of helps, allay the friction, right? So the kind of R and tidyverse evangelists have already sort of made this view kind of very prevalent in the R world more so than in the Python world. But yeah, I think that there does tend to be a lot of differences between code that is developed between our sort of quantitative sciences teams versus the data insight engineers that we work with and the software engineers that we work with, and they might not accept this same sort of paradigm. But I think, again, for our particular team's purposes, because there is such a huge variety of technical skill and technical background, we have people coming really from an epidemiology and biostats background that are really methodological experts, but certainly not coming in with any previous computer science terminology or kind of best practices. And so they may be a little bit more of a blank slate versus others that are coming from more industry data science roles that may be used to doing things a certain way at their previous companies. So we do have a rather long onboarding process and kind of are very standard about this is the style of code that we like to endorse. And we give them a sort of long time to adjust and transition to that. But yeah, I will admit that's a luxury. Anyone else?
Plenty of time.